Hello everyone. In this video, we are going to learn about microservices design pattern, in which we usually have two types of patterns, which is data management pattern and system migration. In the previous video, we saw about microservices versus monolith. But how can we convert a monolith into microservices using decomposition pattern? In that, we saw there are multiple microservices that are created for a single monolith, which might have different databases. Now, after deciding how many microservices we are gonna break down a monolith into, now there are some problems that we face. Okay, let's understand the problem first. Let's say we have a monolith and it is connected to a database. Okay, which means all of the small modules which are present in this one all are accessing the same database. Okay, so they are all modules which are accessing the same database, which means there is no problem when you are trying to access data from this module, and maybe this module is modifying that data, but you are accessing from this module, right? But so once you have broken down into a multiple microservice, then what problems you will face? So whenever we divide monolith into microservices, we usually have a separate database for each microservice, and benefits we already saw in the previous video. So if you know already, then feel free to skip that one. If not, then you should watch that video first in order to understand it much better. Now, the reason for having a different databases for each microservice is that scalability and maintainability. Also, you can have a different type of database for each microservices if the work is such that, right? So we can do that as well. The first problem that will occur, that would be, let's say this microservice wants to access data from this database. So what it will do, it has to ask this microservice to give the data. But if this microservice needs the combination of data from this and this database, now what it will do? There are one way is it will ask for this, and then it will ask for this, and then it will process it, and there will be some resultant output. But it will be too complex, and it will increase latency for our microservice or any operation that we are performing. So it will become a heavy operation. And second, what we saw in the previous one was, if there is an operation coming up that impact multiple microservices database and something breaks in the middle, then how will you fix that, right? Because let's say there is an operation, you modified this service, then you also modified this service, means this database, and then you did to this one. But while you were updating this, there was a problem. Now this has been updated and committed, this also and this also, but this does not, which means data becomes inconsistent. Data goes into inconsistent state. So how will we fix it? Okay, now the third problem, when a monolith is converted into microservices, then the next step is to move all the traffic from a monolith to these microservices. Okay, because you have to move now the traffic, right? You have to replace the modules with microservice. But can you do that in one go? No, you cannot do that, because what if you migrated the whole monolith into this one and something start breaking and you have also deleted this, and now your production is down and your organization is losing a lot of money. So to mitigate that problem, to fix that problem, we have this system migration pattern. Okay, now let's look at that. How does this work? So in system migration, we have a pattern called Strangler pattern. Okay, so this is called Strangler pattern for system migration. In this, what happen is, this is a monolith. Now these are the microservices. Okay, now what will happen? Instead of moving the whole traffic on to the microservices in a one go, we will start, let's say, moving around 1% of 1% of traffic to this module, this microservice. Now there is also a possibility that these microservices are still not completed, only this one is completed. So there is a possibility that for some of the module, for some of the features, microservices development is still in process by other teams or by your team also, but not all microservices are completed, right? Because it's definitely possible, because it depends on organization also, at how big your team is and what you decide, how you decide to develop your microservices. But we are assuming here that only few of the microservices are completed, and you have done the unit testing and integration testing for that, and also development testing. Now what you have, you want to really test that how it perform in the live environment. So what you do, instead of moving whole traffic, you only transfer around, let's say, 1% of the traffic, which means if there is a 1 million records or requests coming for that particular module one, so you are only moving 1% of those requests. That would be very minimal according as compared to 1 million, right? And then you check how this microservice is behaving for that traffic. So if everything goes well, database updates are fine, logs are fine, and there is no errors for all the operations, then you increase it to, let's say, 10%, or maybe let's say you start with 1%, then you do 5%, then you do 10%, and then you do 15%, and gradually you move it to 100%. That's how you completely migrate a monolith into this microservice for that, let's say, one module. Now, strangler means you are strangling that particular module, particular part of that monolith, or a whole monolith in general, by uh, killing it slowly, step by step, by reducing the amount of load it is receiving from live. Okay, you means you are strangling it. But let's say when you move after 1%, you saw 1%, after 1% traffic, it's working fine. But with 5%, it start to break. It start throwing errors. What you do, you immediately cut off the traffic from microservices and you revert it back the traffic to your monolith, and you start debugging what's the problem is, and once you fix it, you try again from 1%, 5%, 10%, such that which, so in that manner you will be able to migrate the whole monolith into microservice. So it will productionize like that. Okay, so this is strangler pattern. So in short, if we have to define strangler pattern, is the technique or the way that we will use to move the monolith into the microservices is told by strangler pattern. Strangler means killing slowly, and here the victim is monolith app by reducing traffic and slowly moving towards microservices. Okay, so this is Strangler. Now we will discuss about data management in microservices. Now this is divided into two parts. There are two types of data management: database for individual service and shared database. Database for individual service means, as we saw already in the above example, each microservice will have its own separate database. Okay, or they both will have their separate database. And for shared one, it is just like monolith, but in microservices, all the microservice will be sharing a same database. And honestly, this is not very useful. It is not considered as useful. This is not successful, and we will see how and why. Okay, let's look at the shared database case. In this one, the problem that we immediately see here is scaling individual database is not possible, because there is no individual database or separate database for each service. So we cannot scale them, which means if, let's say, for this microservice, traffic is higher than other two, and this microservice is causing a lot of stress on database, then we cannot just scale the part where this microservice is operating. Instead, we have to scale up the whole database server, which means these both will also enjoy the resources that we will add for this database. So it is not feasible. And second could be that modification modification in DB of one service will affect other services as well. Means if this microservice is making some schema change for its table, or let's say you have written a liquid script and it starts failing, then these both microservices will also be affected, because the database server will not come up, or also this service will be failing due to it. Or there might be a possibility that you modified some schema for via this service, and that table was also being used by this service, but now since the schema is changed, this service has no clue what has changed, and it starts failing. So means this change caused by this is also affecting these two microservices. So this is another case and issue. But the good part is the joining of the query is fast. Like join query operations are faster. Why? Because there is only single database for all the microservice. You can simply do joins very easily, and it will not cause you any trouble, or it will also not cause you any latency. This is one of the benefit for shared database. Now here with this one, when we are using this particular approach for database for individual microservice, here actually these data management patterns comes into the picture, which is Saga and CQRS, and they both solve different issues for this scenario, and we will look into it. Now since we have a separate database, joining of the queries is not possible, because this literally have a separate server, and you cannot touch or operate directly on the database of another microservice. This is the rules, this is the condition. So we will talk about conditions. Let's talk about conditions first. So in database for individual service, database per service, no service is allowed to query the database of another service. Now, second is service can request other service for some data, but cannot directly touch other service database, which means this service can ask this service to give it some data. It will not directly query this database. Now, third is individual service can have different types of database, since only individual service has to talk with it, right? Let's say you can use SQL for this particular microservice. You can use NoSQL database for this microservice, or maybe you can use time series database for this, right? It doesn't matter, because only this microservice has to talk with this. And if this microservice is only dealing with time series kind of data, let's say trade charts kind of data, where it is saving data based on timestamp or something like that, then using a time series database is more feasible and fast and efficient for this microservice. So it can use that. But in case of shared database, you cannot do that. You are logged with one kind of database that you choose in the start. You cannot migrate to SQL to MySQL. If you even do to if you do migrate from SQL to NoSQL, then all of the microservice will be affected, right? So this is the drawback, and this is the benefit of database per service. And it's actually better, because with this efficiency may be improved and latency may be reduced for database per service. But it raises two issues. One issue is joining the query is not possible. You have to ask other service for the database for the data. Now if there is the data is that kind of complex to process or prepare, then it will increase the latency and overhead, which will in result slow your application rather than improving it. And second problem is, if there is a change that is has to be done across multiple service database, let's say a transaction that is affecting this microservice, this as well, and this as well, and so to manage it, we have to also need something for that, because in case of any failure, in the last or in the middle, we will have inconsistent data, and which we don't want. So we want to fix that problem as well. So that's why there are two patterns that are defined. One is CQRS. CQRS basically solve the joining query problem. It improves it basically, and how we will see. Second is Saga design pattern. This solve the problem when transaction is spanning across multiple microservices. So this is resolved by Saga pattern. Now, what is the advantage of having database per service? So as we saw that there was a problem of scaling, and here there is no such problem. If we observe that if this microservice number 3 suddenly have a spike in traffic or write request or maybe read request, causing database server to run near its maximum capacity, then what we will do, we can scale this single database, and we don't have to worry about other databases. They can be just like that because they are working normally. Or maybe we can scale down certain database if it's not being used that much, so we can do some money saving. Okay, now moving forward, let's talk about first and very important design pattern called Saga design pattern, which is kind of a favorite interview topic for all of the high level system design interviews, and they are asked across for all the experience ranges starting from 4+ years. If you are trying in some product based companies and they are giving anywhere above 24 LPA, 25 LPA, 30, 35 LPA, then this is a very favorite topic. They will ask in microservices. They want to know that do you understand the problem of database and transition. So they will ask you, do you know about Saga pattern? And it's quite crucial for all of us to know that. Now, before directly understanding Saga pattern, we have to understand a certain property of database, which is called asset property. Now, asset property says that either update all or update none, which means let's say there is a database and there are certain rows. This is first row, this is second row, and this is third row. Now you are updating something on this row, you are updating something on this row, and while updating this row, something fails. So according to asset property, these two changes will also be rolled back. Okay, they will be also rolled back. So this means that update all or update none. But in case this was also successful, then commit would have happened and transition would be completed. Okay, now how we will achieve this asset property in case of distributed system where we have multiple microservices and literally we have to touch database of multiple microservices. How we will achieve this asset property, this is our main goal with Saga design pattern. Now what happens is, let's say there is a request from online store and these are microservices for order, inventory and payment. Now you place the order, database updated. Now since you have to reduce the inventory size also, so you touch this database and you inventory is got updated. But now on the payment service, it got failed. Now what it will do, it will roll back all of these three changes that it did. Okay, this will be done by Saga design pattern. And how? Let's look at it. Saga means sequence of local transaction. Means Saga will maintain a sequence, or you can also say that a sequence will be that the transactions would be updated sequentially. So Saga converts the records into sequence of transactions in which the operations are happening, right? So it usually have via event. Some messaging queue we use here. uh, let's say we are using Kafka, which means this particular service after updating its database will publish a message. It will publish a message of success that hey, I have updated my database, then which will be listened by the next microservice in line, and it will perform changes into its database, and it will again message 2 will be published that hey, I have also updated my inventory. Then this will be listened by the final payment microservice, and once the payments is done and completed, it will also publish okay, done, I am also done. So it will also publish this event, and now a success response would be sent to the user. Okay, now let's say something goes wrong. Now payment received it and start processing its payment and it get failed. So what it will do, it will publish a failure message. Hey, I got failed. Now this failure message will be consumed by this service, inventory service. In the same sequence, the success messages was created. In the same sequence, failure message will also be published. Failure events will be also published. So this service will listen to this message. It will also roll back and also publish an event of failure. Now this service will say, oh, okay, something is wrong with inventory. So I have to also roll back the same transaction. So it rolls back and it also publish a message. Okay, I have rolled back, and then a failure to the user. Okay. Now this is called choreography. The thing I just explained is called choreography. There are two types of Saga. One is choreography, and second type of Saga is orchestration. Okay, so in choreography there is one event block in which each service publishes events of success or failure, and accordingly other service will proceed after listening those events. Okay, which means there will be, let's say, queues. There will be two queues. This is, let's say, success and this is failure. So in choreography there will be message events, and there will be two queues, that would be success message queue and failure message queue, and these services will publish success messages to this queue, and also they will listen success messages from this queue. Okay, so they will also listen, they will also publish. All the services will be publishing and listening. So in case of success it will publish, in case of failure also it will publish, and they will listen. Now there is a possibility of circular dependency in this choreography. Let's say if this service does some update and give to this S2, and there's also a possibility that this changes to this, and then again it does something and then change, then again it does something. So, or maybe let's say it's sent to this also and it's sent to this also, it does something change, then again it is waiting for this one, or maybe it is waiting for this one. So there is a possibility of some circular dependency in case of choreography. Now to resolve this, there is a second part that we discussed, was orchestration. Now there is another type of Saga pattern, which is orchestration. So now in orchestration, what happens is there is a server called orchestrator, which handles the sequence of updates in case of transactions where multiple microservices has to update their database. Okay, so this is a new component called orchestrator. Instead of message events that manually calls the services for doing their updates or reverse. Okay, now how does it work? Now let's say some request comes, then this orchestrator will take care of that request, and it will say, hey, update yourself. Once it updates itself, then it will send success message. It will say, okay, I have updated my database and I have successfully done that. Then once it receives success, then it will send to this, and then similarly it will revert back, and then finally here, and it will revert back. Okay, this is first case where everything is success. Now similarly, in second case, what will happen? Let's say this service said, okay, I failed, so it will say, oh, you failed. Then it will say abort, it will send abort message, which means rollback. Then it say, okay, I have rolled back. Then it will say, okay, you also roll back, and then it will say, okay, I have also rolled back. So here it it got fixed. So the possibility of cyclic dependency got removed in the orchestration. So this is another type of Saga pattern. Now let's talk about an interview question that can comes up in this. So let's say there are two people, there are two person one, person one want to send $10 to person two, and we are deducting this person balance from a balance microservice, and payment that we are saying we are sending payment, we are doing it via payment microservice. So this process is maintained by payment microservice. Okay, so let's try to visualize it in a much better way. So let's say there is a request which says pay $10 from person one saying pay $10 to P2. Now what will happen? We have two microservices that will be involved in this scenario. One is balance. So this is one. First, this will happen. Why? It will check and it will deduct the money from the P1's wallet. Okay, so it will say deduct $10. So now total balance for P1 is 100 minus $10, which is 90, and now payment will be recorded via payment service. But while we were recording the payment, it means we were transferring this $10 to P2 account, it got failed. Now how we will manage it? So this is the interview question. So answer for this one would be that the payment service will publish an event, and this event will be listened by the balance service, and it will, what it will do, it will do a rollback. So it will add those $10, making balance back to $100. So how you will say this? You can say, so here you will use Saga, and payment service will publish an failed event, which will be listened by the balance service, and it will reverse the transaction and return $10 back to P1. So this will be the answer for this particular interview question. Now next we have is CQRS. CQRS stands for Command Query Responsibility Segregation. Let's look at the problem. Let's say we have two services, and one service is connected to its database 1, second service is connected to its database second, and now initially what will be happening at service 1 will do all of the update, delete, create and read to its native database, and same service second. But now the problem is, if service 1 wants some data from service 2, or there might be one another service, let's say there is service 3, and let's say there is another service, service 4. Now this service wants to get an data which is combination of all these services. Now as per rule, it cannot touch the database of these individual services directly, but it has to ask them separately, and then it has to process its data, and a response will be shared. Now the problem here is lots of network calls has been increased. You see, it will call this, then the second service will be called, then another fifth service will be called. So like that, there will be quite a lot of network calls. To avoid that, how can we fix? CQRS comes into the picture to solve this problem. It reduces the network latency by segregating responsibility of queries. It says separate the read with writes, which means one model will handle all the reads and rest will handle the create, update and delete. So here what is happening, this service, service 1 and service 2 both do have their individual database, but there is a new database which we are calling read only database or view data, that will have the combination of all of these services data, or we can say a view of their data. Read database will handle all the reads, and this database is will be eventually consistent with the real database, because what we are going to do, we are going to update this database via events. So this database will listen to those events and update it. So this is CQRS. So here we are separating the reads with the writes. So I hope you understand all those patterns for microservices that are present. In case of any query, feel free to comment down and I will try to respond as fast as possible. Thank you. See you in the next one.